Hi, my aim with this series of videos is to teach you the basic theory behind the domain name system, and a little more advanced theory too. This shouldn't require too much specialized background, but a familiarity with the Unix or Linux command line and TCP/IP would be helpful. The material is necessarily slide heavy, but I'll try to jump out of the slides to the command line or the web now and again. Don't feel bad if you need to go back and view a video again. Lord knows how many times I've had to re-record them. By the end of this course, you should understand why DNS was developed, what the DNS namespace, domains, and domain names are, what zones are and how they're related to delegation, what resolvers and name servers are, how resolvers and name servers cooperate in name resolution, the various types of name servers, including primaries, secondaries, caching and authoritative only name servers and forwarders, the syntax and purpose of the most common types of resource records, and finally, how to use nslookup and dig, the most common DNS query tools. Before learning how the domain name system works, it's important to understand a little of its history, including what preceded it and the problems it was designed to solve. That's what we'll look at in this short chapter. Before DNS, back in the time of the ARPANET, there was the host table, often called hosts.txt. This was a single monolithic file that mapped the names of all the hosts on the ARPANET to their IP addresses, and it was maintained by a single organization, the Network Information Center, which was run by SRI International up in Menlo Park, California. It was distributed from a single host called SRI-NIC. Here's a snippet from host.txt. The format isn't too different from the format of the Unix etc hosts file or the Windows host.txt file, if you're familiar with those. Each line contains information about a single host, including its IP address in the second field, the host's canonical or official name in the beginning of the third field, optionally followed by one or more aliases, then the hardware that ran the host, the operating system it ran, and finally, a list of services it supported. The sharp-eyed among you may notice an important nuance about this file. The hosts appear in no particular order, not sorted by IP address or host name. Network administrators on the ARPANET would submit their portions of host.txt to the NIC, which would aggregate them into a single file and make that file available via FTP. As the ARPANET grew, though, this scheme developed all kinds of problems. One was latency. The file was only updated twice a week, so it could be days before your brand new host was actually accessible over the ARPANET. The amount of bandwidth consumed by folks sending updates to the NIC and downloading the host table was considerable. Remember, in the early days, the pipes that constituted the backbone of the ARPANET ran at 56 kilobits per second. Though IP networks could be assigned in a way that allowed network administrators to dole out individual IP addresses without consulting a central authority, host names couldn't be assigned the same way. You had to search the host table for name collisions before naming a host, and all the good names, like Frodo, Bilbo, and Gandalf, were quickly used up. The file got big, too. When I took over HP.com, Hewlett-Packard's internal host table was nearly 100,000 lines long, and the ARPANET's host table was much larger than that. Searching the file took a long time because, of course, you had to search it linearly. It wasn't sorted. And at HP, on some of our slower computers, the search would actually time out before reaching the end of the file. Some administrators took to sorting the file so that frequently looked up hosts were near the top. So work began to design a successor to the host table. Paul Makapetris, then at the University of Southern California's Information Sciences Institute, was largely responsible for the design of the domain name system. The chief design goals were to allow local administration of partitions of an overall host naming database, but to make those partitions available globally, that is, across the entire ARPANET, and to use a hierarchical namespace which would allow easy partitioning of the database and ensure the uniqueness of host names. Here's a look at a timeline of DNS history over the past 30-odd years. You can see that the scale along the horizontal axis is not particularly accurate. The first RFCs, requests for comments documents to describe DNS, were published by Makapetris back in 1983, and the ARPANET made the transition from the host table to DNS between their publication in 1984. In 1984, the first version of Bind, the preeminent open source implementation of the DNS specs, came out. It was Bind 4. Makapetris updated the core DNS RFCs in 1987 to RFCs 1032 through 1034, upon which the current version of DNS is actually still based. The Microsoft DNS server, a popular DNS server that's bundled with Microsoft's Windows Server operating systems, came out in 1993. Bind 8, a rewritten version of Bind, came out in 1997, followed by another major overhaul, Bind 9, in 2000. And we're actually still running versions of Bind 9 on the internet today. Now let's talk a little bit about the theory behind the domain name system. The domain name system is the internet's naming service, and it's responsible for mapping those funny dotted names that you see in email addresses and URLs into IP addresses and other types of data. In an email address, like events@infoblocks.com, the portion that's relevant to DNS is everything that follows the @ sign. So in this case, infoblocks.com. In a URL, like http://www.infoblocks.com/, the portion that's relevant to DNS is everything that follows the first two slashes and then precedes the next slash. In this case, www.infoblocks.com. Human beings find it much easier to remember and work with these names than with IP addresses, particularly IPv6 addresses, which are a whopping 128 bits long. Computers, of course, have no trouble remembering IP addresses, no matter how long they are. But the domain name system is also a distributed database, which is partitioned into things called zones. We'll talk more about zones in an upcoming section. These zones can be managed in a distributed, decentralized way, but the data within those zones can be made available globally across the entire internet. Organizations connected to the internet can manage their own zones almost completely autonomously, and yet the information in those zones can be made available to anyone else. Note how closely this lines up with the original design goals for DNS. No accident there. The domain name system, as I said, is a distributed database, and databases typically have indexes. The domain name system is no different here. In DNS, the indexes are those funny dotted names, which are properly called domain names. And those domain names are actually paths in something called an inverted tree. Inverted trees are a computer science construct. They're similar to a family tree, or if you will, a mobile that hangs from a ceiling. An inverted tree is made up of nodes and of links between those nodes. There's a picture of one, substantially cut down from the real Internet Namespace, on the right side of the slide. Each node is connected to its parent by a single link, and one node can be a parent to arbitrarily many children, which sounds like a social policy nightmare. Each node has a label associated with it, and that label is between 0 and 63 bytes in length. So 0 and 63 characters, generally speaking. The root node, which is way at the top, since it's an inverted tree, has a special reserved label, which is written as a pair of double quotes because it's a 0-length label. You have to imagine the label as being hidden there between those double quotes. Otherwise, though, the main restriction on labels is that all children of a single node have to have different labels. A label is not going to be sufficient to uniquely identify a node in the namespace. In order to do that, uniquely identify a node, you need a list of labels, which is called a node's domain name. It's the series of labels from the node to the root, read with dots separating the labels. Here's a node down at the bottom of the tree. Its domain name would be the label associated with that node, followed by a dot, followed by the label of its parent node, followed by a dot, and so on until you get all the way up to the root node's 0-length label. So here's how you'd read the domain name of my old Unix desktop machine when I worked at Hewlett-Packard. You can see it's down there at the very bottom of the namespace, and its domain name was winnie.corp.hp.com. Occasionally, you'd even see it written with a dot at the very end, that dot being the last separator between the com node's label and the root node's 0-length label. Now let's talk about some topics related to the namespace: domains, subdomains, delegation, and zones. Domains are groups of related nodes. Technically, they're a subtree of the namespace, everything at a particular node of the namespace and below that point. Domains are identified by a domain name. That is the domain name of the node at the apex or top of the subtree. If you look at the diagram on the right, you'll see that we're highlighting a node whose domain name is com. But in addition to identifying that node, that domain name also identifies an entire domain, which consists of all of the nodes at or below com in the namespace, indicated by the red triangle. You could also think of the com domain as consisting of all domain names in the namespace that end in com. hp.com, www.infoblocks.com, and so on. There's a similar concept in DNS called a subdomain, which are domains contained within another domain. If you think back to the last section, where we talked about the similarities between the namespace and a file system, this is much like the relationship between directories and subdirectories. In this case, the apex, or the top of the subdomain, is within its parent domain. If you think of this in terms of the domain names of the domain and one of its subdomains, the name of the subdomain will always end in the name of the parent domain. So, for example, infoblox.com is a subdomain of com because it ends in com. In the diagram on the right, you can see the domain com, and within it, a subdomain whose apex is within the com domain, such as, for example, infoblox.com. A single organization typically runs a domain. For example, an organization called ICANN, the Internet Corporation for Assigned Names and Numbers, runs the root domain. A company called VeriSign runs the com domain. But if you think about this carefully, you may realize that there's a conflict here. The root domain technically includes every node at or below the root node, so it's really the entire namespace. It actually includes the entire com domain. So how can both ICANN and VeriSign control all of the nodes below com? Clearly they can't. That's where delegation comes in. Delegation is a process that allows an organization that manages a domain to assign control of a subdomain to a different organization. Now, rather than containing all of the information in the subdomain, the parent domain only contains pointers to sources of data in the subdomain. We'll talk about what those are in one of the later sections. The parent and child are now separate administrative containers referred to as zones. Here's a diagram showing how delegation creates zones. The red line segments represent delegation. Up at the top, we have the root zone in orange, managed by ICANN, and below it in red, the com zone, managed by VeriSign. Below the com zone, we have lots of delegations, over 100 million of them, believe it or not, to hp.com and infoblox.com and every other two-labeled domain name ending in com that you've ever heard of or typed into a web browser. So far, I've used just a few real domain names from the Internet's namespace, chosen mostly for my own personal or sentimental reasons, like hp.com or infoblox.com. Let's take a brief detour from theory and look more closely at the structure of the Internet's namespace. Initially, the Internet's namespace was simple. There were just 7 top-level domains, and they were organized functionally. Com, for example, was for commercial organizations, such as Hewlett-Packard, which uses hp.com. Edu was for educational organizations, such as my alma mater, the University of California at Berkeley, which uses berkeley.edu. Gov was used by U.S. governmental organizations such as NASA, which uses nasa.gov, and INT for international treaty organizations such as NATO, which uses nato.int. MIL is still used by U.S. military organizations such as the U.S. Air Force, which uses af.mil. NET was used by networking organizations such as NSFNet, which used nsf.net, and org was used by non-commercial organizations, such as the Internet Systems Consortium, which uses isc.org. Many of these original charters have since been relaxed, however. Com, Net, and org were opened in 1996 to any would-be registrant, whether they were networking related or not, non-commercial or not. These were the first of what we now call generic top-level domains, or GTLDs for short. There was also a transitional domain, ARPA, which was used when well-known hosts moved from the host table into DNS. You just tacked .arpa onto the end of the host name to create its new domain name. So for example, the host that was used to distribute the host table, sri-nic, became sri-nic.arpa, and then eventually became nic.ddn.mil. sri-nic.arpa remained as an alias for nic.ddn.mil for some time to make the host easier to find. As with so many transition mechanisms, however, ARPA lasted much longer than was originally intended. In fact, it's still in use today, albeit for different purposes, which we'll look at later. Some of you may note a certain nationalistic prejudice in some of these early top-level domains, such as gov and mil, which are still used almost exclusively by U.S. organizations. You may find it easier to forgive this if you remember that the ARPANET began as a U.S. Department of Defense project. Later, top-level domains were reserved for every country in the world, according to a standard list called ISO 3166. ISO 3166 lists 2- and 3-letter abbreviations for every country in the world. We refer to the domains created from this list as CCTLDs, country code top-level domains. The first 3, US, UK, and IL, for the United States, the United Kingdom, and Israel, were created back in 1985, and at this point, almost all the countries in the world have one registered. ISO 3166 has actually been updated a lot over the past several years. For example, after South Sudan separated from Sudan in 2011, it got a new two-letter country code, SS. While this seems like a really simple scheme, as with all human endeavors, it's more complicated in its implementation. Some obsolete CCTLDs are still in use, such as the Soviet Union's SU, and some countries don't use the two-letter abbreviation from the document, like Great Britain, which should use GB but actually uses UK. ICANN later allowed the addition of more top-level domains. Initially, these were a rather motley collection of oddball domains like Arrow, Biz, Co-op, not Coop, Info, Museum, Name, Pro, and Travel, later supplemented by Cat, Jobs, Moby, and Travel. Cat, somewhat surprisingly, does not host cat videos, but rather serves the Catalan community. The website of beautiful Gaudi Basilica La Sagrada Familia, for example, lives under Cat. Quite recently, ICANN opened up the market for top-level domains to all comers that is, who had nearly $200,000 to apply. They now include everything from adult to church, and from rocks to sucks, and even a top-level domain called Cricket. There are about 500 of these which are due to be added to the top level of the namespace. Now let's take a few minutes to talk about a different kind of top-level domain. In fact, a new kind of label in a domain name. These are internationalized domain names. All of the domain names we've seen so far have used simple ASCII characters in their labels. Again, that's not too surprising given that back when DNS was developed, the early 80s, the internet was but a gleam in the ARPANET's eye, and of course the ARPANET was largely a US project. But today's internet is a global network, and most of the world's inhabitants speak languages that don't use ASCII characters, and there's a new breed of TLDs to serve these folks. These new TLDs may look very foreign to us because, well, they are. They're written in international scripts, using international characters from languages such as Chinese, Japanese, Arabic, and Hebrew. Here are some examples. Here's the Chinese equivalent of gov, the Japanese version of Google, and Arabic for site. Unfortunately, DNS can't accommodate these scripts directly. DNS software assumes, for example, that each byte in a label represents a single character, as in ASCII, but it takes multiple bytes to represent the tens of thousands of characters in the world's languages. So instead, we use an algorithm called Punycode to encode characters from other scripts into ASCII, and then we use the equivalent ASCII string in labels. For example, here are the Punycode encoded equivalents of two of those internationalized TLDs we saw on the last slide. Note that Punycode encoded strings always begin with the 4 characters XN-, which makes them easy to spot. No other labels should start that way. So how does this encoding happen? Most modern web browsers support internationalized domain names, which means that you can enter domain names with labels that include international characters, and they'll automatically translate those labels into the equivalent Punycode strings before querying a DNS server. The DNS server has no idea you've typed a domain name that included Hindi or Urdu, but you get to the website you meant to. Many of these new TLDs are international, that is, they use non-ASCII characters. And now you'll know how to recognize them. So that's the namespace, the abstract structure of the indexes into DNS's distributed database. But aren't there concrete components to DNS too? Database servers, that sort of thing? Yes, there certainly are. The database is stored on servers called name servers, or equivalently, DNS servers. Personally, I prefer name servers, but sometimes DNS servers is clearer. And those name servers are queried by software called resolvers. Together, these comprise the client-server system at the heart of DNS. Clearly, no one name server has enough capacity to hold the entire internet's namespace. And you might remember that we broke the namespace up into administrative units called zones using delegation. Well, those zones are what name servers load. Some name servers don't load any zones. We'll describe how those can still be useful later. Other name servers load thousands of zones. When a name server has all of the data in a particular zone, we say it's authoritative for that zone, or that it has authority for the zone. That name server can then answer any query about any domain name in the zone. Name servers are responsible for answering queries sent by resolvers, the client half of DNS, but also by other name servers. See, DNS isn't just a simple client-server system where the only communication is between client and server. Sometimes the servers talk to other servers too. Resolvers are the client half of the domain name system. But what are they actually? Like name servers, they're software. But resolvers aren't usually a separate piece of software like a name server or a web server. Usually, they're part of a device's operating system, part of Windows or Mac OS X or Linux or iOS. Even simpler devices that support DNS lookups also have resolvers, generally built into their system software or firmware. What's the resolver for? Operating systems exist primarily to run applications, and those applications often need to look up data stored in DNS. The resolver gives them an easy way to do that. Resolvers take applications' requests for data in DNS and translate them into DNS queries. The resolver awaits a response, and it may have to retransmit the query. If it times out, it may fall back to querying a different name server if the first one isn't responsive, or it may fall back to using a completely different name service. When it receives a response, the resolver will unmarshal that into a data structure and pass that data structure back to the application. Why is that necessary? Well, the low-level format of a DNS message is fairly nasty, variable length and binary. Just putting together a syntactically correct query would take a detailed understanding of the DNS protocol, and most application developers would rather not be forced to become experts in DNS just to look up the address of www.google.com. So resolvers, in many cases, are just libraries of software routines that abstract the low-level details of assembling a query, sending it to a name server, maybe resending it, and extracting the interesting part of a response. An application developer calls a friendly-sounding routine, such as getHostByName, passing it the domain name whose address he's interested in. He gets back a data structure that contains the IP address or addresses that the domain name maps to. So we have name servers that load some zones, maybe thousands of zones, but certainly just a sliver of the Internet's whole namespace. We have resolvers that may ask those name servers about arbitrary domain names, without regard to which zones those name servers are authoritative for. How's that going to work? Conveniently, the namespace is organized as an inverted tree, and resolvers specify the domain name they're interested in their queries. So a name server can start at the top of the tree and work its way down till it finds the name servers it's after. What does it mean to start at the top of the tree? Well, we talked a while ago about the root zone. There's a set of name servers authoritative for the root zone, not unexpectedly referred to as the root name servers. We can query them for any domain name. Unless we're asking for data in the root zone itself, they won't know the answer, but at least they'll be able to refer us to the name servers authoritative for the next zone down the chain, probably a top-level zone. And then we can ask them, and so on. Query, refer, repeat. Eventually, by following a series of referrals, the name server reaches the name servers authoritative for the zone that contains the domain name it's after, and queries one of them. This time, instead of returning a referral, the authoritative name server simply answers the question. Then, of course, the first name server, the one that did all the work, following referrals, relays that answer to the resolver. This process, whereby one name server queries a series of other name servers to find arbitrary data in the namespace, is called resolution. Here's an example of resolution. The resolver over there on the left side of the slide is going to resolve www.infoblocks.com by querying the name server that's in the middle. In the very center of the slide, you can see the root name servers, the com name servers, and the infoblocks.com name servers, which are all going to play a part in this resolution exercise. And over on the far right, a diagram of the namespace. We're going to try to show how the various queries and referrals correspond to traversing that namespace. So resolution begins when the resolver over there on the left sends a query to its name server for www.infoblocks.com's IP address. That name server, not having any more specific information about www.infoblocks.com, starts by querying one of the root name servers. And he asks that root name server for the address of www.infoblocks.com. So we're starting, over here on the right, at the very top of the namespace. Now, the root name server probably doesn't know the address of www.infoblocks.com, but it can, at the very least, send a referral to the com name servers. So the name server in the center follows up on that. It chooses one of the com name servers to query, and it asks it for the address of www.infoblocks.com. That com name server probably, again, doesn't know the address of www.infoblocks.com, but at least it'll know where the infoblocks.com name servers are. So over on the right, in the namespace diagram, you'll see that's like traversing the link between com and infoblocks.com. Our name server follows up on that by choosing one of the infoblocks.com name servers to query, asking it, finally, for the address of www.infoblocks.com. This time, however, the authoritative name server knows the answer and simply returns that answer to the name server. and it relays that answer eventually to the resolver. Now let's get back to that issue of work. The first name server query, the one that's sort of left of center in this diagram, the one that the resolver sent its query to, wound up doing much more work than the other name servers. It followed several referrals to find an answer, whereas the other name servers involved just sent referrals when they didn't know the answer. Why did they get off so easy? The difference is the kind of query they were handling. The first name server received a recursive query from the resolver. Accepting a recursive query obliges a name server to do all the work necessary to find the answer, which might include following several referrals. In particular, a name server that accepts a recursive query may not send a referral as a response. Most resolvers send recursive queries specifically because they lack the ability to follow referrals. They're just not smart enough to. Most name servers, on the other hand, are plenty smart enough to follow referrals, so they send non-recursive queries by default. That gives the name servers that receive them the option to reply with referrals. In fact, it's beneficial to name servers to send non-recursive queries because those referrals contain valuable information about the namespace, as we'll see shortly. This is probably a good time to give you a little more detail about DNS queries and responses. Both DNS queries and responses are DNS messages, and they share a common format. Both are usually based on UDP, the User Datagram Protocol, which is an unreliable transport protocol. That means that resolvers and name servers must take into account the possibility of packet loss and retransmit when necessary. Queries and responses both begin with a header, followed by a question section, and responses may include an answer section, an authority section, and an additional data section. The header and the question are always present, yes, even in a response. But whether the other sections are present or not depends on a few factors, like whether the response is an answer or a referral. The header includes an opcode, which for queries and responses is just query. We'll talk about other kinds of DNS messages that use other opcodes later. There's also a QR bit, which is 0 for a query and 1 for a response. And there's an RD bit, which stands for recursion desired. That determines whether this is a recursive query or not. In recursive queries, it's 1. In non-recursive queries, it's 0. The question section contains information about the query, specifically the domain name, the class of data, and the type of data the querier is interested in. The domain name, of course, identifies the domain name in the namespace the querier is interested in: www.infoblocks.com, www.google.com, isc.org. It could be the domain name from a URL, or on the right side of the @ sign in an email address. The class is almost always IN for Internet. The type indicates which of the various types of data stored in the namespace the querier is after: an IPv4 address, an IPv6 address, mail routing information, and so on. A brief note on class. DNS was designed with the idea that it could accommodate different kinds of networks, not just TCP/IP-based internets. Those other kinds of networks would have used different classes. But the use of DNS with other kinds of networks never really took off, maybe because TCP/IP became so dominant. So except for a very small number of special cases, class is always IN for Internet. The answer, authority, and additional sections are just there to carry data in the form of resource records. That's what we store in the namespace, resource records, or RRs for short. All those domain names, just indexes pointing to resource records. So in a response to a query about the IPv6 addresses of www.infoblocks.com, the authoritative name server for infoblocks.com will add resource records to the answer section, telling the querier those IPv6 addresses. The full resolution process we went through may seem awfully involved to some of you. If you're resolving www.infoblocks.com to an IPv4 or IPv6 address over and over, and I certainly hope you are, does your name server really have to follow 2 referrals each time? No, because after your name server has looked up the address of www.infoblocks.com once and followed those 2 referrals, one from a root name server and one from a COM name server, it'll cache the resource records in those referrals. Specifically, it'll cache the names and addresses of the COM name servers and the names and addresses of the infoblocks.com name servers. It'll also cache the answer, the address of www.infoblocks.com. Let's see how that helps streamline the resolution process for future queries. Let's say you query your name server again for the address of www.infoblocks.com. Your name server has already cached the resource records answering the question, in which case it can simply return the answer without asking anyone. If you query your name server for the address of support.infoblox.com, it may not have that record cached, but it's already learned the names and addresses of the infoblox.com name servers, so it can skip querying the root name servers and the com name servers and go directly to the infoblox.com name servers, which should reply with an answer. Even if you send your name server a query for hp.com, the cached data helps a little. Your name server can skip querying the root name servers because it already knows where the com name servers are. They, of course, will refer your name server to the hp.com name servers. It'll follow up, query them, and get the answer. Of course, you can't cache resource records forever, because sooner or later someone might need to change the address of a web server or add or decommission a name server. So each resource record, as we'll see shortly, carries a value called its time to live, which tells a name server how long it can cache it. TTLs typically range from seconds to hours to days, and it's the administrator of the zone that contains the resource record that decides on that record's TTL. The name server caches a record and decrements its TTL over time. Once the TTL reaches 0, the name server deletes the record. Keep in mind that the TTL doesn't have any effect on a name server that's authoritative for the zone that contains the resource record. It doesn't decrement the TTL. Only name servers that cache that record do. In our example of resolution, we simplified the scenario somewhat. Simplified with all those referrals? Yep. Virtually all zones have more than one name server, for example, so it's up to the name server handling the recursive query to choose which root name server to query, which com name server, and so on. Also, since DNS queries and responses are usually sent over UDP, it's possible that they won't arrive. So the recursive name server may need to retransmit queries. Resolvers may have to retransmit queries too. Let's talk about server selection first. The various makes and models of name servers choose which name server to query based on different algorithms. The open source bind name server, one of the most popular implementations, uses an algorithm based on round trip time. Basically, bind name servers time how long it takes for remote name servers to respond to queries, and then remember that. Whenever a bind name server has a choice of authoritative name servers to query, it'll query the one that responded the most quickly in the past. If it's never queried a name server before, it just gives it a random low round trip time. Low, so it'll at least try querying it before starting to play favorites, and random, so that it doesn't try all of the authoritative name servers for a zone in the same order as every other bind name server. The algorithm, which has been around since the beginning of bind, back in the 80s, is remarkably effective. Like server selection, retransmission algorithms are also dependent on the name server implementation. But all name servers send queries, await a response, and retransmit if they don't hear back within some timeout. Given a choice of authoritative name servers to query, they'll usually choose another to query rather than retransmitting to an unresponsive name server. Bind will keep trying the authoritative name servers for a zone for tens of seconds before giving up. Now it's time to talk about the various types of name servers. We've already seen examples of name servers in action, and we've introduced concepts including authority, recursion, and caching. Those three concepts give us the names of these first three types of name servers. First is an authoritative name server. As the term suggests, this is a name server that's authoritative for one or more zones. Unfortunately, that doesn't narrow the field much. Almost every name server is authoritative for at least a few zones. What most folks mean when they refer to an authoritative name server is a name server whose main function is to answer non-recursive queries for domain names in zones that it's authoritative for, as opposed to a name server whose main function is to perform recursion to find data stored on other name servers. Some authoritative name servers even have recursion disabled, so that if they receive a recursive query, they treat it as though it were a non-recursive query. The other situation in which authoritative name server is meaningful is when you specify the zone or zones that it's authoritative for. When you specify the authoritative name servers for infoblox.com, we know exactly which name servers you mean. A recursive name server, on the other hand, is one that is willing to handle recursive queries. It'll do all the work necessary to find the answer, as we saw in the section on recursion. But virtually all recursive name servers also cache their responses, both referrals and answers, that they receive from other name servers. So they're sometimes called caching name servers too. The two terms are basically interchangeable. Some recursive name servers are basically dedicated to the task of performing recursion. They're not authoritative for any zones, or just a handful of built-in zones like the one that maps the loopback address to localhost. These are often called caching-only name servers. Some may be authoritative for many zones, though. What do you call those? The recursive name server, also authoritative for foo.example and var.example? That's pretty unwieldy. Sometimes we refer to them according to context. Just the foo.example name server if it's answering non-recursive queries in foo.example, or the recursive name server if it's handling recursive queries for www.google.com. Authoritative name servers come in two subspecies, primaries and secondaries. The difference is where they get their zone data. A primary, like the one on the left side of the slide, reads zone data from a file, cleverly called a zone data file. A secondary, like the one on the right side of the slide, transfers its zone data from another authoritative name server, often the zone's primary, but sometimes another secondary. This mechanism is called, wait for it, a zone transfer. Just like queries and responses, zone transfers are carried in DNS messages. In fact, a zone transfer is really just a special case of a query that can generate a large response, one that's often carried in a series of DNS messages over TCP instead of UDP. The secondary initiates the zone transfer by sending its master server, the authoritative name server that it's configured to pull zones from, a query with a special type called IXFR. The master responds by sending the resource records in the zone. After the secondary has a copy of the zone, it checks with its master periodically at what's called the refresh interval to determine whether the zone is changed. Each zone contains a single serial number that's increased anytime its data changes. If the serial number on the master is higher than the serial number on the secondary requests a zone transfer. On the right side of the slide, you see this in progress. First, you see the secondary name server send a query for the SOA record for the zone, which contains the serial number. The primary responds with the serial number, and the secondary compares the serial number in the primary's response to the one that it holds in its secondary copy of the zone. If they're up to date, the secondary waits for the refresh interval to pass and then checks again. This time, if the serial number in the SOA record indicates that the zone data has changed, it'll turn around and request a zone transfer. There's no difference in authority between a primary and a secondary. Just as a primary marks a response that it sends from its zone data as authoritative, so does a secondary. In fact, if you look at a set of authoritative name servers for a zone on the internet, you can't always tell which one the primary is. For example, which of these 13 root name servers is the primary? I'll give you a hint. It's none of them. In practice, DNS provides primaries and secondaries to make it easier to run multiple authoritative name servers for a zone. For robustness and performance, zones need at least 2 and possibly many more authoritative name servers. It's much easier to use the built-in zone transfer mechanism to replicate zone data instead of coming up with your own means. It's a little silly to call a particular name server a primary or a secondary without specifying which zone you're referring to. A single name server can be primary for some zones and secondary for others. In common usage, though, a primary name server is one that's primary for most of the zones it's authoritative for, and a secondary is one that's secondary for most of its authoritative zones. One thing primary and secondary do not mean, however, is the first or second name server that your resolver queries. That's a common misuse of the terms, and it's very confusing because primary and secondary have established semantics. Remember this example of recursion? Well, that's the default behavior. Configure a recursive name server with a list of root name servers, and that's what it does. But there's an alternate form of resolution called forwarding. In forwarding, instead of the recursive name server following a series of referrals to find the authoritative name server that knows the answer it's after, it's lazy. If the recursive name server doesn't know the answer already, from authoritative zone data or cache, it just passes the buck by sending a recursive query to another name server, called its forwarder. Assuming the forwarder accepts the recursive query, it's up to the forwarder to send queries and follow referrals as necessary till it finds the answer, and then relay that answer to the first name server. Here's a diagram showing how forwarding works. The name server that's towards the left is configured to use the name server that's just to the right of center as a forwarder. The resolver starts the process by sending a recursive query to the first name server. That name server forwards that query as a recursive query to the forwarder. The forwarder is then responsible for querying a root name server, following a referral from that root name server, querying a com name server, and then following a referral from that com name server, and then finally querying an infoblox.com name server and accepting the answer from it. It then completes the resolution by relaying that answer to the first name server, which in turn relays that to the resolver. Note that the terminology is backwards. The forwarder is the name server that receives the forwarded query. The way English usually works, if you make a noun out of a verb by adding ER, you're referring to a person or thing that performs that action. A worker works, a hunter hunts, and so on. But a forwarder doesn't forward queries. It receives queries that have been forwarded. What do we call the name server that forwards the queries? Well, you could call it a forwarding name server. I've heard that a few times, but I don't think there is an official term for it. What's forwarding useful for? Originally, in the early days of DNS, it gave administrators a way to funnel their queries through a single super name server, which would build up a rich cache of data. But today, it's most commonly used inside a company's internet firewall. Rather than poking holes through the firewall to allow all internal name servers to query name servers on the internet directly, most internal name servers are configured to forward queries to a few designated forwarders. Those forwarders are allowed to send queries to internet name servers. By using the forwarders, all the internal name servers are able to resolve internet domain names, but not all name servers are exposed directly to the internet. The two most popular implementations of a DNS server are Bind and the Windows DNS Server. Bind, released in 1984, is the more venerable of the two. The Windows DNS Server came out over a decade later, in 1996. Let's talk a little more about these name servers and a few others. The Bind name server was written at my alma mater, the University of California at Berkeley, hence the B in its name. Bind is an acronym for Berkeley Internet Name Domain. Version 4 was the first release. The developers were trying to sync up version numbers with other software being released in BSD Unix. Bind is open source, originally released under the BSD license. Maintenance of Bind passed from Berkeley to ISC, the Internet Software Consortium, in the 1990s. ISC released a rewritten version of Bind called Bind 8 in 1997, again, trying to sync release numbers with other software. And they released another rewrite called Bind 9 in 2000. ISC still maintains Bind. The current release, as I'm recording, is 9.10. The Windows DNS Server is shipped with all Windows Server operating systems, undergoing major updates with Windows 2000 Server, Windows Server 2003, Windows Server 2008 R2, and Windows Server 2012. I'm fairly sure that they used to call it the Microsoft DNS Server, and somewhere along the line they changed the name. Bind is famously configurable, having accreted features over the past 30 years. It's usually configured from a text file called named.conf by default. Bind is also enormously popular, powering a double-digit percentage of the name servers on the internet. The Windows DNS Server ships with a graphical user interface for managing DNS called the DNS Manager. The Windows DNS Server integrates with Microsoft's Active Directory, or AD, can store files in AD and read its configuration from AD. Both Bind and the Windows DNS Server can function as recursive name servers, authoritative name servers, or both at the same time. More recently, some specialized name servers have been developed that support only recursion or authority. Two of the best come from NLNet Labs, a Dutch nonprofit organization. Their recursive name server is called Unbound, and their authoritative name server is called NSD. Back when we were discussing resolution, we mentioned resource records, or RRs for short. These are the units of data stored in the DNS namespace. They map domain names to IP addresses, mail routing information, and more. Referrals consist of resource records. But what do resource records look like? Inside a DNS message, resource records appear in a binary format, but in zone data files, and in the output of better DNS query tools, they often appear in a textual format called presentation format or master file format. Let's look at that format. Resource records in presentation format begin with a domain name, which is the domain name in the namespace to which the record is attached. If that domain name ends in a dot, it's absolute, written relative to the root of the namespace, a bit like a path name in a file system that begins with a slash or backslash. If it doesn't end in a dot, it's relative and may have another domain name called the origin appended to it. By default, the origin in a zone data file is just the domain name of the zone, so this makes abbreviating domain names convenient. In the zone data file for infoblox.com, you can write www and it's interpreted as www.infoblox.com. There's also a special symbol, @ that you can use instead of a domain name to indicate the domain name of the origin itself. The name is followed by some whitespace and then optionally the time to live, or TTL, of the record. We talked about this back when we introduced caching. This is how long recursive name servers can cache this record. TTL is natively an integer number of seconds, but most name servers let you use scaled values, such as 1H for 1 hour, or 10M for 10 minutes, or even 1H 30M for 1 hour and 30 minutes. Values are commonly minutes or hours, but for some types of records, you'll even see days. If an explicit TTL isn't included, the record gets a default TTL. After the optional TTL comes another optional field, class. Class, as I said before, is almost always IN for Internet, so that's the default. Following the class is the type of record, a mnemonic indicating what type of data is stored by this record. And after type comes what's called RData, or record-specific data. The format of the RData depends on the class and type. For example, an A record, which stores an IPv4 address, in the IN class requires a dotted octet representation of an IPv4 address as its RData. An MX record for mail routing requires a 16-bit preference value followed by the domain name of a mail exchanger. You can see a couple examples of resource records in presentation format towards the bottom of the slide. These use different owner name formats, including a trailing dot and no trailing dot, an integer number of seconds for the TTL, and a scaled value. One last general note about resource records. If you hang out too much with the wrong kind of people, namely DNS geeks, you may hear the term resource record set, or RRset. A resource record set is simply a set of resource records that share the same domain name, class, and type. Why does an RRset deserve a special name? Because they're inseparable. They're generally grouped together in zone data files for administrative convenience, but they're always returned together, since there's no way to specify that you only want the first or second A record for www.infoblox.com. The most common, and arguably the most important record type is the A record. The A originally stood for address, and it's tempting to call A records address records, but the pedantic IPv6 evangelists among us, yours truly included, would point out that they're really IPv4 address records. IPv6 addresses use a different type. Here's the presentation format for the A record. It takes as its record-specific data a single IPv4 address in dotted octet notation. Simple enough. How do you attach multiple IPv4 addresses to a single domain name, as you might want to for a router or multi-homed host? You simply attach multiple A records to the same domain name. How do you know which address an application will use first when it looks up the domain name? Well, it's generally the first one returned. Some applications try to choose among a list of addresses, but not many. Most these days will cycle through addresses if there are more than one. Wait, is the first one that appears in a zone data file the first one returned? Not necessarily. We'll talk soon about RRset ordering, and you'll see how the order can be configured and how it can change. The IPv6 equivalent to the A record is the quad A record, which has the type mnemonic AAAA. It has 4 A's because a 128-bit IPv6 address is 4 times as long as the 32-bit IPv4 address in an A record. You pronounce it quad A, not if you want to hang out in a DNS-savvy crowd. The only real difference between the A record and the quad A record is the record-specific data. Quad A records require a single IPv6 address in the RData in that colon-separated format that you've probably become familiar with. If you want to attach multiple IPv6 addresses to a domain name, you use multiple quad A records, just as you would with A records. If you attach both A and quad A records to the same domain name, which one gets used first? Again, that depends on the client. Some clients will always use one record type before the other, typically quad A before A. Other clients look up both simultaneously and will try to connect both IPv4 and IPv6 addresses if they're available, essentially racing the two protocols against each other to see which connection completes first, then using that one. This algorithm is known as happy eyeballs. The PTR, or pointer record, is chiefly used for mapping IP addresses, both IPv4 and IPv6, back to domain names. This is sometimes referred to as reverse mapping. When you think about it, the A and quad A records aren't useful for reverse mapping. Sure, it's easy to find an IP address given a domain name, but what if you're given an IP address to start with? You can't easily do an exhaustive search of the namespace for the domain name that points to that address. Instead, there's a special part of the namespace in which the octets of an IPv4 address or the hexadecimal digits of an IPv6 address are used as the labels of domain names. That makes it easy to determine which domain name to look up when you're given an IP address. And the type of record you look up for that domain name is a pointer record. The part of the namespace in question is the old ARPA top-level domain, the one originally used as a transition tool from the host table to DNS. ARPA has two subdomains used for reverse mapping: in-adder.arpa, which is used for reverse mapping IPv4 addresses, and ip6.arpa, which is used for reverse mapping IPv6 addresses. Under in-adder.arpa, the labels of the domain name are the octets of the IPv4 address in reverse order. For example, to reverse map the IPv4 address 50.19.85.84, up at the top of the slide, you'd look up pointer records for the domain name 84.85.19.50.inadder.arpa. Why are the octets reversed? That's so delegation under in-adder.arpa works sensibly. IP address space is delegated hierarchically. For example, HP runs the network 15/8, which is all of the IPv4 addresses that begin with the octet 15. So it makes sense to delegate 15.in-adder.arpa to folks at HP, but that means that the first octet of the address comes last in the domain name. Under ip6.arpa, the labels of the domain name are the hexadecimal digits of the IPv6 address in reverse order, for the same reason as in in-adder.arpa. To reverse map the IPv6 address 2406:DA00::FF00::3213:5554, which you see in the middle of the slide, you'd look up pointer records for, well, I won't read it to you, but it's right there, an enormous long string that starts 4555. Note that you have to expand the : in the IPv6 address, which is a shorthand for a string of zeros, into their explicit zero values. So you end up with an owner name that has a whopping 34 labels in it. Here's the full presentation format for the pointer record. The owner names are as described, and the record-specific data is a single domain name, that domain name that you want the IP address to reverse map to. What's reverse mapping used for? Well, some server software reverse maps IP addresses to log the domain names of clients that connect. Some server software even reverse maps IP addresses to domain names to check whether clients are authorized, though that's not a particularly good idea. Note that you can attach multiple pointer records to a single domain name, but as with A and Quad A records, there's no guarantee of the order in which the records will be returned. Many clients that use pointer records don't expect more than one, and therefore don't search through them, so this may not work reliably. The CNAME record creates an alias in DNS. The alias is the domain name to which the record is attached. The target of the alias, sometimes called the official or canonical name, hence CNAME, is the record-specific data. Here's an example of one. The alias is the name alias on the left-hand side, and the target of the alias, the canonical name, is official.infoblox.com. CNAME records are singleton records. If a domain name has a CNAME record attached to it, it may not have any other records attached. That makes sense when you think about it, since by saying that a given domain name is an alias for another, the CNAME record is also saying that all those other records should be attached to the canonical name, not the alias. The way CNAME records are processed is different from the way most other records are processed, since a querier doesn't usually know ahead of time that a domain name is an alias. The querier may ask for an A record for the alias, for example, and an explicit search for an A record won't find one because it's attached to the canonical name. So the authoritative name server that receives a query for any type of record for a domain name and doesn't find one will then look for a CNAME record. If the CNAME record exists, regardless of the type sought in the query, the authoritative name server will return it. When the recursive name server sees the CNAME record, it'll restart the query, replacing the alias with the canonical name. So to go back to our original example, once a recursive name server looking up A records for the name alias finds out it's an alias for canonical.infoblox.com, it'll restart the query looking up A records for canonical.infoblox.com. Consequently, it's a bad idea to chain aliases, A to B, B to C, and so on, because of the work involved in resolution. The MX, or Mail Exchanger record, is used by mail servers, technically SMTP Mail Transport Agents, or MTAs for short, to determine where to send electronic mail. The format of the MX record is fairly simple. The owner name is a domain name that appears to the right of the @ in an email address. The record's specific data consists of two fields: preference value, which is an unsigned 16-bit number written in decimal, so between 0 and 65,535, and the domain name of mail exchanger. Here's an example of one, bottom of the slide. A mail exchanger is a mail server that accepts mail addressed to the domain name that owns the MX record. Accepts could mean that it delivers mail to its recipient, or that it simply relays the mail to another mail server. The preference is an indication of the desirability of delivering mail to the corresponding mail exchanger. Lower preference values indicate more preferred mail exchangers. Since preference is unsigned, that means that 0 is the most preferred. Here's how MTAs determine how to deliver mail addressed to a user at some non-local domain name. First, the MTA looks up the MX records for that domain name. Then it sorts the MX records highest preference, that is, lowest preference number, to lowest. The MTA looks for the domain name of the host it's running on in the list. If it finds itself, it removes that MX record as well as any MX records with an equal or lower preference. That's to avoid loops. Clearly, sending mail to itself won't help get mail delivered, and sending the mail to a less preferred mail exchanger is simply moving it farther from its destination. Now it should have a list of MX records. If there aren't any left, that's an error. The MTA tries to deliver the mail to the most preferred remaining mail exchanger. If there's more than one that are most preferred, it can choose among them. If delivery fails, it must try all the mail exchangers at that preference before trying any less preferred mail exchangers. One last note, if a mail exchanger tries looking up MX records for a destination and doesn't find any, it'll usually try looking up A and Quad A records for the destination too, and treating any it finds as equal preference mail exchangers. MX records are only useful for delivery of email using SMTP, the Simple Mail Transport Protocol. But some aspects of the MX records functionality, like being able to designate a backup server or multiple servers for a service, would be useful for other protocols too. Enter the SRV, or service record. It's like a general-purpose MX record that can work with any service. The syntax of the SRV record is a little more complicated than the MX record. The record's specific data has 4 fields. Priority, a 16-bit value, which works like preference in MX records. Wait, also a 16-bit value, which is used for distribution of load. Port, which tells clients which port the service is running on. And target, which gives clients the domain name of a host offering the service. SRV records also sport owner names with an unusual format, as you can see at the bottom of the slide. The first 2 labels of the domain name are the name of the service and the transport protocol it runs over, both with leading underscores. The rest of the domain name is the domain name that the client actually specified. So, for example, if you're using a web browser that looks up SRV records and type http://www.infoblocks.com, the browser should look up SRV records for the domain name _http://tcp.www.infoblocks.com. How are all those fields used? An SRV Smart client would look up SRV records for a destination before looking up Simple A or Quad A records. If it found SRV records, it would sort them according to priority, highest priority to lowest, just like MX records. It would then try connecting to the highest priority target on the port specified. And if it found more than one SRV record at the same priority, it would connect to the targets in proportion to their weight fields. For example, a client would try 2 equal priority, equally weighted targets with equal probability. Basically, the client would flip a coin and go to target 1 on heads and target 2 on tails. If there were 3 equal priority, equally weighted targets, it would throw a 3-sided coin, or choose a random number between 1 and 3, whatever. If one target had a weight that was twice that of the other, the client would try the first target twice as often as the second. As with preferences in MX records, clients must try all targets at a given priority before trying less preferred targets. Which clients support SRV records? Truthfully, not a lot. Some notable exceptions? Computers that are members of an Active Directory domain find their domain controllers by looking up SRV records. And, my daughter will be so pleased, Minecraft clients find servers that way too. The TXT, or text record, can be used to attach comments or almost anything else to domain names in the namespace. Here's its presentation format. The type field is TXT, and the record-specific data is one or more double-quoted strings. Technically, the R data doesn't need to be double-quoted, but then it's interpreted as a series of double-quoted strings, which is a little weird, so best to quote it. At the bottom, you see an example of a text record that's used in something called SPF, Sender Policy Framework. We'll explain that in a later chapter. You can safely use any ASCII string in the R data. Each string can be 255 bytes long, and you can use multiple strings to specify even longer data. However, it's a good idea to stay under certain limits. Text records larger than 4K won't fit into most UDP-based DNS messages, and text records longer than 1300 bytes will be fragmented at the Ethernet layer, so it's wise to keep your R data shorter than that. In this lesson, we're going to talk about infrastructure records, the SOA record, the NS record, and glue. Some records are used primarily by DNS itself, not by hosts or applications running on those hosts. These are SOA and NS records. SOA stands for Start of Authority. There's only one SOA record for a zone, and it's attached to the domain name of the zone. The SOA record contains important zone parameters, including the zone's serial number, which we talked about way back when we discussed primary and secondary name servers. NS, or name server records, list the authoritative name servers for a zone. As with the SOA record, the owner name must be the domain name of a zone, while the record-specific data lists the domain name of a name server authoritative for that zone. When an authoritative name server needs to tell a recursive name server which name servers are authoritative for a zone, as in a referral, it does that by sending NS records. Here's the format of an SOA record. The owner name is the domain name of a zone, and there are 7 record-specific data fields: the mname field, the rname field, the zone's serial number, the refresh interval, retry interval, and expire interval, and finally, the negative caching time to live value. Here at the bottom of the slide is an example of an SOA record. Note that we're using a special format here. The last character of the first line of the record is an open parentheses, which tells the name server reading the record to ignore carriage returns and new lines from there to the matching close parenthesis on the last line. You can use these parentheses in any type of record, but SOA records are so long that you'll routinely see parentheses in them. The mname field, by convention, contains the domain name of the primary name server for the zone. Some software that sends dynamic updates to name servers looks at this field to help decide where to send those updates. But if a zone isn't dynamically updated, it doesn't matter much what you put there. The rname field, also by convention, contains the email address of a person responsible for the zone. The email address is in a funny format, though. The @ sign is replaced by a dot, so dns@infoblox.com becomes dns.infoblox.com. Only human beings, and maybe some spam miners, actually use this field. But it's considered polite to list a real address here so folks having trouble with your zone can track you down. The serial number, refresh, retry, and expire intervals all have to do with transfers of the zone, and we'll discuss them on the next slide. The negative caching time to live value determines how long recursive name servers may cache negative responses from the name servers for the zone. There are 2 negative responses in DNS. NX domain, which means the domain name you asked about doesn't exist, and no data, which means the type of record you asked for doesn't exist for that domain name, though the domain name itself exists. When a name server sends either type of negative response, it usually includes the zone's SOA record in the message, so the recipient name server can see how long to cache it. Serial numbers are unsigned 32-bit values, used as an indication of the version of the data in a zone. Whenever a zone's data changes, the serial number is supposed to increment. That way, a secondary name server for the zone can tell that it needs to do a transfer to update its copy. Many folks use a format like YYYYMMDDVV for the 4-digit year, followed by the 2-digit month, 2-digit date, and a 2-digit version. They do that if they only edit the zone data by hand. This allows for about 100 updates a day, which is quite a few if you're maintaining a zone manually. For zones that are updated automatically via dynamic update or rewritten by scripts, the serial number just doesn't usually have a fixed format. Secondary name servers compare serial numbers using something called sequence space or clock arithmetic. Think of a time on a clock, say 11:30 p.m. Given another time on the clock, how can you tell whether that time is before or after 11:30 p.m.? 11:45 p.m. seems later, but what about 12 a.m., 3:30 p.m.? For convenience, we'll just stipulate that the next 12 hours even if they wrap around past midnight to the next day, are later, and the previous 12 hours are earlier. So 11:45 and 12 a.m., that is midnight, are later, but 3:30 p.m. is earlier. Serial numbers are compared the same way. For a given serial number, the following 2 to the 31st values, half of the sequence space, even if they wrap around the maximum 32-bit number back to 0, are considered bigger, while the previous 2 to the 31st values are smaller. Here's how serial numbers are used in action. Remember this slide? The secondary checks to see if its master server has a higher serial number for the zone. In this case, it looks at the serial number and determines that it hasn't changed, so it waits for the refresh interval to pass, then checks again. This time, the zone serial number on the master is higher, presumably because someone modified the zone, so it requests a zone transfer to bring it up to date. Let's say the refresh query fails for some reason. Maybe the master doesn't respond. Then the secondary waits for the retry interval, which is usually shorter than the refresh interval, before checking again. The idea is that after a refresh failure, the secondary should try more aggressively. If the expire interval passes, and the secondary is unable to determine whether the zone data is up to date or not, it stops answering queries for data in the zone, figuring that the data is now so old that it can't give it out safely. As you might imagine, the expire interval is usually many multiples of the refresh interval. After expiring the zone, the secondary name server starts responding to queries for data in the zone with an error known as serve_fail, or server failed. On to the NS record. Here's the NS record's presentation format. Again, like the SOA record, it's always attached to the domain name of a zone. The record's specific data is the domain name of a name server authoritative for that zone. Since most zones have more than one authoritative name server, they'll also have more than one NS record. NS records stitch the namespace together. Back when we showed the links between zones, those were really NS records. Whenever an authoritative name server refers a recursive name server to name servers authoritative for some subzone, it sends a list of NS records for that subzone. Even the root hints, the list of name servers authoritative for the root zone, are expressed as a set of NS records, along with their corresponding A and quad A records. Here's the top of the Internet's current root hints file. Note the NS record pointing to a.root-servers.net. Those A and quad A records are important, critical in fact. That's because the NS records alone aren't enough. You know the name of the name server you need to query, but not its address, and you need an address to send the query to. Those accompanying A and quad A records are the glue that completes the delegation. Here's the real delegation from the com zone to the infoblox.com zone. It's useless as is because there are no addresses. And to find the addresses, a recursive name server would need to query those same infoblox.com name servers. A real chicken and egg problem. So to solve the problem, the parent zone contains A and quad A records for those name servers, even though normally you'd find those records in the infoblox.com zone, not com. Note that glue address records are only necessary when the domain name of the name server being delegated to ends in the domain name of the zone being delegated. Otherwise, a recursive name server could find the address of the name server by querying other name servers. Wildcards are actually not a record type, but rather a special type of label in a domain name. Instead of attaching a record to an explicit domain name, a record can match queries for a whole bunch of domain names. The wildcard is the asterisk character, and must be the first label of the domain name. Here's an example. A wildcard in infoblox.com, star.infoblox.com. The wildcard matches one or more labels in a domain name being looked up, but only if a more specific match isn't present in the zone. Let's say you have these records in the zone. An A record attached to the apex, www owning a CNAME record, test being delegated to ns1.test.infoblox.com, and then finally a wildcard record. The wildcard would match a query for foo.infoblox.com because that doesn't exist in the zone, or foo.bar.infoblox.com because that doesn't exist in the zone, but not infoblox.com or www.infoblox.com, which clearly both exist in the zone. Or, in fact, for foo.test.infoblox.com, since a delegation to test.infoblox.com exists. You can almost think of a wildcard as a default name in the zone. You can use wildcards with many types of records, including A records, quad A records, MX records, and CNAME records. Wildcards don't make much sense with SOA and NS records since they must be attached to a zone. the wildcard will only match queries for the same type as the type the wildcard owns, except for wildcard CNAME records, which of course will match any type and restart the query. Wildcards often change the result of other query types, however, since in a zone with a wildcard, all domain names seem to exist. Consequently, authoritative name servers for that zone don't send NX domain responses, just no data responses. When a query matches a wildcard, the authoritative name server synthesizes a new record with the domain name in the query and the right side of the wildcard record. The wildcard itself isn't returned. So a query for foo.bar.infoblocks.com against the wildcard in the previous slide would return an A record for foo.bar.infoblocks.com pointing to 10.0.0.1, not the wildcard record. An RRset, you'll remember, is all of the records attached to a particular domain name of the same class and type. For example, all the A records for www.infoblocks.com are an RRset. So are the MX records for infoblocks.com. Name servers may vary the order in which they return the records in an RRset. The three most common RRset orders are round robin, also known as cyclic, in which the first record returned is rotated to the end of the list after each response, random, in which the records are returned in a random order, and fixed, in which the records are always returned in the same order, usually the order in which they appear in the zone data file. Here's an example of round robin or cyclic at work. See how the first record returned in the first response becomes the last record returned in the second? In the next response, 10.0.1.1 would be rotated to the end, so 10.0.2.1 would become the first record returned. Some folks try to use RRset order to spread load among a set of servers, say web servers. The problem is that your name servers probably have no idea of the load on those servers, or even whether they're up or down. And other name servers, such as local recursive name servers, may reorder the records too. And some clients may not simply use the first record returned, in which case all bets are off. Let's see how those records work in recursive name resolution on the actual internet. To do that, we're going to use a DNS query tool called dig. We'll cover dig in more detail in a later chapter. For now, I'll try to explain the queries I'm sending and point out the important records in the responses. Let's start by looking up quad A records for the domain name www.infoblocks.com, a domain name I'm sure you're sick of at this point. We're going to use one of those root name servers that we saw at the beginning of the root hints file, a.root-servers.net. We also have to specify quad A for the type of query, and of course the domain name that we're interested in. Finally, we're going to specify plus no rec, which means send a non-recursive query to the name server, which we would do if we were acting as a recursive name server. Got a lot of output here, some of it scrolled off. Note what we get here is a big authority section containing 13 records, all of them NS records for COM. This is delegation. We're being delegated from the root name servers to the COM name servers, and you can see they have names like a.gtld-servers.net through m.gtld-servers.net. The additional section of the DNS message includes address records, both IPv4 and IPv6 for each of these servers. So let's follow that referral. In order to do that, we're going to have to change the domain name of the name server that we're querying to a.gtld-servers.net. Now, of course, if we were a real recursive name server doing this, we'd choose according to round trip time or some other algorithm. Since it's just me, I'm going to choose the first one. Now, the output is a little more manageable. You can see we get an authority section, which contains 4 NS records pointing to the 4 name servers for infoblocks.com, ns1 through ns4.infoblocks.com. And in the additional data section, we get a bunch of address records, both A and quad A records, showing that we have IPv4 and IPv6 addresses for these name servers. We'll follow up on that referral, and we will send a query to, let's say, ns2.infoblocks.com for that quad A record. And what do we get? A quad A record in response? No, as a matter of fact, we get a CNAME record. Well, it turns out that www.infoblocks.com is actually an alias for a big, long string that ends in, not surprisingly, AmazonAWS.com. Amazon Web Services is hosting our web server. So now we have to restart the query manually. And instead of looking up the address or quad A record for www.infoblocks.com, we have to look up the quad A record for this big, long string, which I don't want to try to type manually because I'm just not that good of a typist. So we'll paste it in there. And we have to start over at the root name servers too, because of course ns2.infoblox.com really isn't going to know much of anything about AmazonAWS.com. So we'll replace ns2.infoblox.com with a.root-servers.net and resend our non-recursive query. And what do we get? Well, the same thing that we got before when we asked for www.infoblox.com, a referral to the com name servers. In fact, we could have reused those because they would have been in our cache, but I guess my cache isn't that large. Let's go back. We're going to swap a.root-servers.net for a.gtld-servers.net. Ask one of those com name servers the same question. And we get a referral to the AmazonAWS.com name servers. So let's follow up on that referral. Let's choose one of those. Let's say r1.amazonaws.com. We send our query and we get another referral, this time to the four name servers authoritative for us-east-1.elb.amazonaws.com. Let's choose the shortest of these to type in, ns-235. And what do we get? Aha! Finally, we get an answer. 2 Quad A records giving us the 2 IPv6 addresses for www.infoblox.com. So you can see that there is actually a lot involved in following an alias. There's a lot involved, in fact, in just resolving a domain name. But remember that after our name server has done this once, it'll have cached all of these records according to the time to live on the records. Now let's try looking up something that doesn't work so you can see what that looks like. Let's look up cricket.infoblox.com's A record. What do we get? If you look in the header, you'll see here an NX domain status. That means this domain name does not exist. The domain name that you asked about does not exist. And remember I said in those negative responses, you receive in the authority section the SOA record for the zone that would have contained the domain name. And remember at the end, we have the negative caching TTL, which is 3600. The number of seconds that you can remember the fact that cricket.infoblox.com doesn't exist. As we discussed, stub resolvers, the client side of DNS, will retransmit queries if a name server doesn't respond, and will fall back from one name server to another if configured with multiple name servers. The details of how and when a resolver does this, however, are dependent on the make and model of resolver. Take, for example, the bind resolver, which is included as part of many Unix and Linux-ish operating systems. You can generally configure a bind resolver to query up to 3 name servers, though on some operating systems, the limit is higher. The resolver starts by querying the first name server in the list and waits up to 5 seconds for a reply. If it doesn't get one, it tries the next name server in the list, again waiting 5 seconds for a reply. If it queries all the name servers in the list once without receiving a response, it doubles the 5-second timeout, divides by the number of name servers in the list, and starts at the top of the list again with the new timeout. Newer bind name servers only go through the list twice. Altogether, that ends up looking like this table. You can see that with a single name server, the timeout starts at 5 seconds, then doubles to 10. With 3 name servers, the timeout starts at 5 seconds, then changes to 3 seconds. The aggregate timeout, if no name servers respond, is between 15 and 24 seconds. That may seem like a long time, but remember that name servers usually respond very, very quickly, in a fraction of a second, so you normally won't have to wait that long. The Windows resolver is a very different animal. Of course, the Windows resolver ships with Windows operating systems, but there are different species in different versions of Windows, even in different service packs of the same version of Windows. And like some wild animals, the Windows resolver is very aggressive. Here are the timeouts for various versions of the Windows resolver. Notice how much shorter the timeouts are than the bind resolvers. 1 second, 1 second, 2 seconds, 2 seconds. It also retries more, for a total of 4 retries. That's not the full account of its aggressiveness, though. On Unix and Linux-ish operating systems, the whole operating system has a single resolver configuration. Windows can have a different resolver configuration per network adapter. Each network adapter may have a different list of name servers. And on modern networks, many computers have at least one wired and one wireless network adapter. Windows also doesn't restrict itself to trying a single name server. It may shotgun queries to multiple name servers at once, and it doesn't always run through the list of name servers from top to bottom either. If a name server doesn't reply, Windows will move it to the end of the list for that network adapter. Here's a quick look at the configuration of the Windows resolver, specifically in Windows 7, in case you haven't seen it for a while or have never seen it. Notice that this is the resolver configuration for the LAN adapter. Much of the time, that configuration will be handed out by a DHCP server, but you can also override those settings here. If you want fine-grained control over resolver configuration, you can configure them here in the advanced TCP/IP settings. Given all these per adapter lists of name servers, and the rotation of unresponsive name servers to the end of each list, what does the combined algorithm look like? Well, it goes something like this. First, the resolver queries the top name server on the preferred network adapters list and waits up to the first timeout. That's generally 1 second. If it doesn't respond, the resolver rotates that name server to the end of that list and queries the top name server on all network adapters lists. It waits up to the second timeout. If none of these respond, the resolver rotates all those name servers to the end of their respective lists and queries the top name server on all adapters lists again. It waits up to the third timeout. If none respond, the resolver, really desperate by now, shotguns the query to all of the name servers on all of the adapters lists simultaneously. It waits up to the fourth timeout and then does it again. The good news is that the aggregate timeout is only 15 seconds in the worst case. The bad news is that if your DNS infrastructure starts slowing down, your Windows resolvers are going to start shotgunning queries around, making recursive name servers resolve the same domain names in parallel. And that's going to exacerbate the problem by slowing your name servers even further. Remember that domain names that end in a dot are considered absolute, relative to the root. That's true both for zone data files and for resolvers. But how does a resolver complete a potentially incomplete name typed at the command line or in an address bar? There are two mechanisms for doing this, and which one is used depends on the context. The first is the local domain, a single domain name that's the domain that the resolver is in, or the domain that it does most of its lookups in. The second is the search list. This is a list of domain names appended to possibly incomplete names. The local domain is used to interpret single label domain names in configuration files. If you have foo in a host.equiv or .rhosts file, you obviously don't mean every host on the internet with the first label foo. You mean foo in your local domain. The search list is often applied by network clients, such as SSH clients or web browsers, to complete possibly incomplete names typed as arguments or in the address bar. The elements of the search list are appended to the name in order, and the result is looked up until an answer, usually an address, is found. Different resolvers have different rules as to when the argument is looked up as is, but they typically involve counting the number of dots in the argument and using that to decide whether the user actually typed the fully qualified domain name but neglected to add a trailing dot. Clearly, long search lists can result in unnecessary queries, so it's a good idea to keep them short. With the bind resolver, you can either set the local domain and make do with the default search list, or set the search list explicitly. Here are a couple of examples. Domain nxdomain.com sets the local domain as nxdomain.com and sets the search list to the default. Search inca.infoblox.com explicitly sets the search list to those two domain names in that order. And it also sets the default domain or local domain to inca.infoblox.com. The default search list includes just the local domain, and an explicit search list is limited to 6 domain names and 255 characters. If you're approaching that limit, there's a good chance that you're doing something wrong. The bind resolver decides whether to look up an argument as is by checking the number of dots in the name. By default, if the name has at least 1 dot, it's looked up as is first, before applying the search list, but you can configure that threshold. The Windows resolver will set its local domain to the same name as the Active Directory domain that it's part of. If it's not part of an Active Directory domain, you can set it manually or through DHCP or global policy. By default, the search list is derived from the local domain to include the local domain and all ancestor names with at least 2 labels. So, for example, if a Windows resolver's local domain were ad.infoblox.com, its default search list would be ad.infoblox.com, then infoblox.com. And just as network adapters can have their own set of name servers, they can also have their own domain names, which are added to the search list. These are typically referred to as connection-specific DNS suffixes in Microsoft's terms. Here are a couple of screen grabs from Windows 7 showing parts of the resolver's configuration, which may be scattered around the user interface. On the left, you'll see where you set the primary DNS suffix, Microsoft's term for the local domain. On the right, you see checkboxes that control what goes into the search list. By default, both local and connection-specific domains, as well as the ancestors of the local domain. Finally, here's where the connection-specific domain is configured. Time was, the only way to update zone data was to edit a zone data file and then reload the zone. That required either an administrator's manual intervention or stream editing the file, which was a little dicey. One mistake and the zone wouldn't load, and your name servers would start spewing serve fail errors. The internet needed a way within the DNS protocol to add resource records to and delete records from a zone. So RFC 2136 was published in 1997, and Dynamic Update was born. Like DNS queries and responses, updates are carried in DNS messages and identified with a unique opcode, update. Updaters, which can be any devices with the appropriate code, not necessarily a name server, send updates to the authoritative name servers for a zone to add records to or delete records from it. The sections of the DNS message after the header are repurposed as the zone, prerequisite, and update sections. The zone section simply contains the SOA record of the zone to update. The prerequisite section contains an optional set of conditions which, if included, must be true in order for the subsequent update to be processed. There are 5 types of prerequisites: that an RRset exists, which is value independent. For example, www.infoblocks.com has at least one A record. That an RRset exists, but the value is dependent. So, for example, that www.infoblocks.com exists and has an A record that points to 10.0.0.1. That an RRset does not exist, for example, that www.infoblocks.com has no A records. That a name is in use, for example, www.infoblocks.com has at least one resource record associated with it. And then finally, that a name is not in use, for example, that www.infoblocks.com doesn't own any resource records whatsoever. There are 4 types of updates that you can perform. You can add resource records to a resource record set. You can delete an entire RR set, for example, all of the A records for www.infoblocks.com. You can delete all RR sets from a name. So, for example, delete all of the records of any type from www.infoblocks.com. And you can delete a particular RR from an RR set. For example, you can delete only the address record for www.infoblocks.com that points to 10.0.0.1. So together, you can construct useful updates like this. Add a quad A record for host1.nxdomain.com only if host1.nxdomain.com doesn't already own any quad A records. Add an MX record for nxdomain.com at preference 20, pointing to smtp2.nxdomain.com, but only if there's an existing MX record for nxdomain.com at preference 10, pointing to smtp1.nxdomain.com. Or if there are any A records for host2.nxdomain.com, delete them. Of course, the updater is not required to set prerequisites, in which case the update is processed, that is, assuming the updater is authorized. Now, the updater can't just send the update anywhere. Only the primary name server for a zone can update that zone. So updaters follow a process to try to ascertain which name server to send an update to. First, they find the enclosing zone for the domain name to be updated. They do this by sending an SOA record for the domain name that they're trying to update. If the domain name is the name of a zone, this will return the zone's SOA record. If the domain name is just a name in the zone, this will return a negative response, but the authority section of that negative response should include the enclosing zone's SOA record. Either way, you figure out which zone that domain name is part of. Next, look up the NS records for the zone. Compare the NS records to the contents of the SOA record's mname field. If the mname matches one of the name servers in the NS records, that's probably the primary. So put it at the top of the list of name servers to send the updates to. Add the name servers for the rest of the NS records to that list. Then run through the list of authoritative name servers, trying to send the update to each one until you succeed. You can see that for dynamically updated zones, that convention of listing the primary in the mname field can actually be pretty important. What happens if a secondary listed in the NS records receives an update? Well, some secondaries may have update forwarding enabled, in which case they'll forward updates to their master. Otherwise, they'll just refuse the update. A name server capable of processing an update by either updating the zone or forwarding the update sends back a response code indicating success. How is dynamic update used? Well, Windows computers can use dynamic update to register their name to address mappings by dynamically adding A records. Statically addressed computers will also use dynamic update to add pointer records to reverse map their addresses back to domain names. DHCP clients, however, will let a DHCP server add pointer records on their behalf. What about non-Windows computers? Well, some DHCP servers will use dynamic update to add both A and PTR records on their client's behalf. The ISC DHCP server, for example, does this. In fact, it'll add both A and PTR records even for Windows clients, though you can configure it not to. I mentioned authorization of updaters just briefly earlier. Updaters may be authorized by IP address, though. Given the fact that updates are usually UDP-based, that's not very secure. DNS also supports an authentication mechanism called TSIG, or transaction signatures, in which a cryptographic key is shared between the updater and the primary name server processing that update. Updaters can be authorized by TSIG key too. Given that TSIG requires a shared key, it's useful for configuring one or a few DHCP servers and a primary name server with shared keys, but configuring a large population of updaters, say all your Windows computers, with unique keys that they share with the primary is unwieldy. Consequently, Microsoft came up with a variant of TSIG they called GSS TSIG. GSS TSIG uses the keys already stored in Active Directory for every member computer to negotiate a shared secret between a member and a Microsoft DNS server. Microsoft refers to updates secured with GSS TSIG as secure dynamic updates. With the advent of dynamic update, zone data could change much more frequently than before. Computers could register themselves when they booted or received DHCP leases, but secondary name servers would only pick up changes to the zone synchronously when their refresh timers expired. That could mean a substantial wait before all of the authoritative name servers for a zone had new dynamic data. So along with dynamic update came Notify, codified in RFC 1996 and published in, appropriately, the year 1996. Notify allows an authoritative name server for a zone to tell its secondaries when the zone data has changed, so they don't need to wait for the full refresh interval to pass. The primary sends Notify messages whenever it loads a new version of a zone or processes a dynamic update. Secondaries handle receiving a Notify message from their master server the same way they would handle the refresh timer going off. They turn around and query the master for the SOA record for the zone, then check the serial number to see if it's incremented. If it has, they request zone transfers. To address situations in which secondaries get their zone transfers from other secondaries send Notify messages too. All the authoritative name servers for a zone send Notify messages to all the name servers in the list of NS records, except themselves, of course, and any name server also listed in the mname field, since that's presumably the primary. The net effect is a kind of flood-fill algorithm. Secondaries ignore Notify messages from many name servers but their configured master name server or servers, though. Here's an example of Notify at work in a zone transfer dependency graph that has secondaries transferring from other secondaries. You can see the secondary at the bottom of the slide gets his zone transfers from the secondary immediately above him. This assumes that the primary is listed in the mname field. So the primary processes a dynamic update or reloads the zone data, and he sends Notify messages to everybody in the list of NS records, except, of course, to himself. The three first-tier secondaries accept that Notify message, but the one at the bottom does not because it's receiving the Notify message from a name server other than its master for the zone. Once the secondaries in the middle have done their zone transfers, they've got change data too. So they're going to send Notify messages to everybody but the primary and themselves. Here's the one on the left sending Notify messages. But all of its Notify messages are going to be refused because none of those other three name servers use the name server on the left as their master. The one in the middle then sends Notify messages. Two of those are refused by the left and the rightmost secondary, but the one at the bottom secondary is accepted because the middle secondary is the master server for the secondary at the bottom. The rightmost secondary sends his Notify messages, all of which are refused. And then after doing the zone transfer, second-tier secondary at the very bottom is going to send Notify messages to the other secondaries as well, but those will, of course, all be refused. Now, this may look like a whole lot of extra traffic, but you really don't have to worry about it much because Notify messages are very small, just a single UDP datagram. Dynamic updates, together with Notify, meant the possibility of much more frequent zone transfers. Unfortunately, traditional zone transfers carry the entire zone, even if you just add or delete one record. Enter incremental zone transfer, or IXFR, defined in RFC 1995, which was published in 1996. In IXFR, zone transfers can carry just the changes to a zone. In IXFR, a secondary name server sends a query type of IXFR instead of AXFR for the domain name of the zone, and it includes the SOA record it holds for the zone in the query. The master name server then determines what changed between that version of the zone and the current one, what was added and what was deleted. If those changes are larger than the zone, or if it can't determine the changes, it just sends the entire zone. Otherwise, it sends only those changes, a delta. Of course, this requires that master name servers track which changes to the zone correspond to which serial numbers. In the best case, the deltas are very small and may fit into a single UDP-based DNS message, which makes for very efficient zone transfers. This is a bit of a digression from the previous topics, but it's an interesting one in my opinion. Sender Policy Framework is an application of DNS in an effort to combat the spoofing of electronic mail. The standard email sending protocol on the Internet, the Simple Mail Transfer Protocol, or SMTP, doesn't provide any way to authenticate the sender of an email message. A sender can claim to be sending email from whitehouse.gov, even though his IP address is in Moldova, or his mail server has a domain name that ends in .su, the TLD for the old Soviet Union. Sender Policy Framework allows the administrator of a zone to list the domain names or IP addresses of mail servers that are authorized to send mail from the domain names in the zone. This data is added to text records attached to the domain names that appear on the right side of email addresses. The syntax is fairly simple. Here's an example. The top text record is the one that's consumed by SPF. You can see that the R data begins with V equals SPF1, which distinguishes a text record meant for consumption by SPF smart mail servers from other text records that you might use. The next term, the plus MX mechanism, allows any mail servers listed in MX records for the domain name to also send email addressed from the domain name. You can see the two MX records below. Together, mx1.infoblocks.com and mx2.infoblocks.com would be authorized to send email from infoblocks.com addresses. The A mechanism explicitly allows the host with the address that smtp.infoblocks.com maps to send mail from infoblocks.com addresses. And the -all mechanism says that no one else is authorized to send such email. Each mechanism can begin with a plus or a minus. Plus, which is the default, means that hosts matching the mechanism are authorized. Minus, obviously, means that matching hosts aren't. Here's a complete list of mechanisms. All always matches. IP4 matches an IPv4 address or range in network/prefix length format. IP6 matches an IPv6 address or range, again in network/prefix length format. A matches any IPv4 addresses in A records for the current domain or the domain name argument. MX matches the IPv4 addresses of mail exchangers for the current domain or the domain name argument. PTR, or pointer, in which the IPv4 address of the sender is reverse mapped to a domain name, and then that domain name is mapped to an IPv4 address. The two must match, the IPv4 address from which he connected and the IPv4 address to which the domain name maps, and the domain name must end in either the current domain or the domain name argument. Exists matches if the domain name argument owns at least one A record, and include, which processes the SPF text record or records attached to the domain name argument. This is pretty handy when you have multiple domain names that use the same set of authorized senders. If you set up lots of SPF records, who's going to use them? Well, there's actually substantial support for SPF. Lots of software, including Microsoft Exchange and SendMail, support SPF, but you may need to patch them in order to add that support. The big internet email providers also support SPF, including Gmail, Yahoo Mail, Hotmail, and Outlook. Let's spend a little time talking about nslookup. nslookup is a standard DNS query tool, one of the oldest, used to send queries to name servers and print responses. But truthfully, it's not a very good tool. Why is that? Well, it's prone to printing misleading errors. For example, some versions of nslookup, when they start up, try to reverse map the IP address of the name server they're going to query to a domain name, simply to print it in a banner. In some of those versions, if the reverse mapping fails, won't even query that name server. Others will print an ominous-looking error just because the reverse mapping fails, not because there's anything wrong with the query that you intended to send. And that's just one of its idiosyncrasies. I'll point out others. As a consequence, many DNS experts don't like nslookup much. Then why cover it? Well, it's pervasive. Almost every version of Windows includes nslookup, as do most versions of Linux and Unix. So you'd better know how to use it, at least to do the basics. So I'm going to show you nslookups interactive mode. This is a version of nslookup running on a FreeBSD server that I have here. It's a very recent version. It doesn't even print a banner by default. To see the banner, you have to type set all. You can see the name server it's sending queries to by default after default server. This ought to print the domain name of the name server The reverse mapping failed, however, so we just see its IP address, and that's certainly better than having it not query that name server at all. Older versions of nslookup might have printed an error or even refused to query the name server. Then you see the IP address and the port of the name server that you're querying. Below, there's a bunch of information about the query that you'll be sending, including the query type, which by default is A, the search list, and so on. I'll show you how to set these later. For now, let's send a few queries. First, we'll look up our good old standby, www.infoblox.com. Note the trailing dot that says don't apply the search list, though nslookup wouldn't have anyway because there are 2 dots in the string between www and infoblox and between infoblox and com. Since the query type is address, I'm going to look up A records. And you can see we get some output here. We get a non-authoritative answer telling us that www.infoblox.com is in fact an alias for a big long string that starts with dual stack and ends in elb.amazonaws.com. And then we get a couple of addresses for that big long string, dualstack.blah.blah.amazonaws.com. One pointing to 50.16.235.193, one pointing to 50.19.85.84. A couple of things to point out. First, this says non-authoritative answer. That means this is a cached answer. It comes from the cache of our local recursive name server. Also, note that the output is not in presentation format. The alias, which is a CNAME record in actuality, is printed as canonical space name, and we have an equal sign and a bunch of other stuff that has no business in presentation format. The A records are also interpreted. So nslookup is trying to do this to make this easily digestible for the user, but in fact, it's a little bit obnoxious because it means you can't easily copy that and then reuse it somewhere. Now let's enter one of those IP addresses, 50.19.85.84, say. We hit return, and what comes back towards the middle says, here's another non-authoritative answer. That IP address reverse maps to ec2-50-19-85-84.compute-1.amazonaws.com. Note again, not presentation format. You can see, though, that nslookup was smart enough to identify the fact that I typed in an IP version 4 address, and it inverted the octets of that IP address, tacked on in-adder.arpa, and even though the query type was set to address, looked up a pointer record for that. That's helpful, but possibly misleading. I've actually had people swear to me that you can reverse map an IP address just by querying a name server for that address as a domain name, because they saw nslookup do it. Now, of course, you can do this the long way, too. You can manually set the query type to PTR and look up the inverted address with in-adder.arpa on the end. Now let's set the query type to something else. Let's look up MX record. I'll use the set command to do that. I can set any option by typing set and the option name. For Boolean options, you simply type set and the option name to set it, and set no and then the option name to unset it. For example, set recurse or set no recurse, all one word. For options that take a value, you type set option name equals and then the value. So for example, set query type equal to MX. You can also abbreviate options to their shortest unique prefix. So query type can become just Q, which is what a lot of people use and what I'm using right here today. We're going to look up MX records for nxdomain.com. We can see that there's one MX record for nxdomain.com at the bottom, pointing to bigmo.nxdomain.com at preference 1. Another thing to point out here, it doesn't say non-authoritative answer. That's because this is an authoritative answer. That's very subtle. It's the absence of non-authoritative answer that tells you that it's an authoritative answer. So this is another quibble that a lot of us purists have with old nslookup. And of course, again, it's not presentation format. Now, surely we're not limited to querying just the servers in our resolver's configuration. No, you can use the server command to switch your server to another one. Let's say we want to query one of the root name servers, a.root-servers.net. We can do that. The roots don't do recursion, so we'll have to set recursion off. We do that by saying set no recurse, and then we type nxdomain.com and see what kind of a referral we'd get. Sure enough, here's the referral. A bunch of com name servers as well as their corresponding A records and one quad A record. Let's go through all of nslookups options. Here's a list of the options. You can see query type or type, which sets the type of the query. By default, it's A for address. Recurse, which sets recursion on or off. By default, recursion is on. VC, which tells nslookup to use TCP-based queries. By default, it's no VC, which means use UDP-based queries. Search list, which sets the search list. By default, that's set from the resolver configuration. Use a slash to separate elements of the search list. Search, which tells nslookup to apply the search list. By default, that's on. Timeout, which sets the initial timeout between queries. By default, that's 0. I believe that means the initial timeout is set from the system resolver, but I'm not sure about that. Retry, which sets the number of query retries nslookup will send. By default, that's 3. Debug and debug level 2, which sets debugging on. Also, debug level 2 sets super verbose debugging. That's actually kind of handy because it'll show you the various sections of the DNS message, which we've seen before, and it'll show records in something much closer to presentation format. And then finally, ndots, which controls the threshold when domain names are looked up as is before having the search list applied to them. Finally, let's look at nslookups non-interactive mode. To do this, we're going to switch back to our shell. nslookup allows you to specify all of those set options at the command line too, by just using the option name as a command line option with a dash in front of it. The first non-option argument is the domain name you want to look up, and the second, if you use one, is the domain name or IP address of the server you want to query. If you leave it out, nslookup will just use the resolver's configuration to figure out which name server to query. So let's reproduce the various queries that we sent using the interactive mode. nslookup www.infoblocks.com of course, looks up address records for www.infoblocks.com. Using the default name server. You can see we get the same answer there. nslookup 50.19.85.84 reverse maps that IP address back to a domain name. And nslookup-q equals mx nxdomain.com. We'll look up mx records for nxdomain.com. And then finally, that last query, the one that we sent to the root name server, becomes nslookup-no-recurse www.infoblocks.com a.root-servers.net. We get no answer to that one, and the reason for that is because nslookup doesn't believe that the referral that we received merits printing unless we turn debugging on. And then, if you scroll back a little bit, you can see that it does actually interpret that. Now let's talk about dig. Dig is another DNS query tool, a competitor to nslookup. The name is supposed to be an acronym for Domain Information Groper, though that's always sounded reverse engineered to me. Dig is all command line based with no interactive mode whatsoever. Dig has quite a few advantages over nslookup. It prints all sections of the DNS message by default, including the header. It prints resource records in their presentation format by default, so you can copy them, modify them, and use them in zone data. And it also has some cool features that nslookup doesn't have. But dig doesn't come on as many platforms as nslookup does. To remedy this, I'm including a URL here at the bottom of the slide for the bind distribution, pre-compiled on Windows. You can download it, extract the dig binary, and throw away the rest, like grabbing the Sunday funnies out of the paper and throwing the rest away. Dig's basic syntax is very simple. Dig at some name server, domain name, and type. But you can vary the order of the arguments to your heart's content, which is really handy. Dig always knows you're specifying the server to query when you type the @ sign, followed by a domain name or an IP address, and there's almost no overlap between record types and legal domain names, except for TLDs like Mexico's MX, and I'll tell you how to deal with that. The default name server is, of course, the first one in your resolver's configuration. The default type is A, and there's even a default domain name, the root. Like nslookup, dig makes it easy to reverse map IP addresses. You use the -x command line option, followed by an IPv4 or IPv6 address. Here's a list of the most useful dig options, according to me anyway. There's -t, which allows you to explicitly set the query type. You might have to do this if, for example, you need to disambiguate MX, the query type, from MX, the top-level domain for Mexico. -q allows you to explicitly set the domain name to query. Again, most of the time you won't have to do this, but sometimes, for disambiguation's sake, you would. -x allows you to reverse map the option argument's IPv4 or IPv6 address to a domain name. Plus TCP or plus no TCP tells dig to send TCP-based queries or UDP-based queries, and of course, by default, it sends UDP-based queries for everything but zone transfers. Plus domain sets the default domain. plus search or plus no search, very much like nslookups search argument, tells dig to apply the search list or not to apply the search list. Plus recurse or plus no recurse tells dig to either send recursive queries or send non-recursive queries. Plus short or plus no short tells dig to send concise output to standard out versus very short output. Plus time, plus tries, and plus n dots set the timeout, the number of queries dig sends, and the threshold for the number of dots in a domain name to be looked up first before applying the search list. And you can see the defaults over on the right-hand side. Now let's see dig in action. First, I'll send the same queries I did with nslookup in the previous section so you can compare it to dig. We'll look up IPv4 addresses for www.infoblocks.com, and again, add the trailing dots so we don't apply the search list. And you can see the output is significantly different from what we saw in nslookup. First of all, we get a little recap of what's going on here. In the header, this is a query that we're sending. The flags include that this is a response to a query that dig is interpreting. Recursion was desired and recursion was available. There was one question being asked in the query section, 3 records in the answer section, 4 in the authority section, and 1 in the additional section. There's a little opt sudo section here, which says that we're using eDNS0 and advertising that we can accept DNS messages that are as large as 4096 bytes. And the questions section, question that we asked was for A records for www.infoblocks.com. And the answer section should look pretty familiar. This is the non-interpreted version of the output that we saw from nslookup. A CNAME record pointing www.infoblocks.com to that dual stack.blah.blah.blah.amazonaws.com mumbo jumbo, and then 2 address records for that long string ending in amazonaws.com. The authority section, which I don't think we even saw in the nslookup output, and we probably wouldn't have seen unless we had turned debugging output on. And then at the end, we get a little timing information too, how long the response took after the query to be returned, which server we queried, and a timestamp, as well as the size of the DNS message that we received. If we really weren't interested in all of that, we could use the plus short option to get a abridged version of that output. Now let's reverse map one of those IP addresses, 50.19.85.84, back to a domain name. You can see we also get that header, but the gist of what we're after is in the answer section here, which is a pointer record mapping 84.85.19.50.in-adder.arpa back to ec2-50-19-85-84.compute-1.amazonaws.com. You can see we can even see the TTL here, 300 seconds. So all the detail is here for us to use. I think the next thing that we looked up was MX records for nxdomain.com. Here we can type it as mx.nxdomain.com or dig.nxdomain.com mx, whichever we'd prefer. Now we get an authoritative answer flag in the header, indicating that the name server that we queried was actually authoritative for the zone that contained the answer. And in the answer section, you can see the one MX record pointing with value 1, preference 1 to bigmo.nxdomain.com. Pretty cool. Now, I believe we also tried to look up a non-recursive query on a.root-servers.net for www.infoblocks.com, so we can do the same thing with dig. The output is so long that it scrolls off the top, but we can scroll back. You can see that in the authority section, we get 13 NS records for the COM zone, pointing us to the COM name servers a through m.gtld-servers.net. And down below in the additional data section, we get a whole passel of A and quad A records for those GTLD servers. Finally, here are a few tricks that are tough or impossible to do with nslookup. Remember when we traced resolution of a domain name from the root down following referrals? That's really handy if you're trying to troubleshoot a resolution failure. That's built into dig. We can type dig plus trace www.infoblocks.com, and dig will start at one of the root name servers and keep following referrals until it reaches the infoblocks.com name servers and finds the result. So let's scroll back a little bit here. You can see here's the original dig plus trace command. We query one of these root name servers. We actually use our default name server to find the current list of root name servers. We query that root name server. We get a referral to the COM name servers. And from the COM name servers, we get a referral to the infoblocks.com name servers. And then from those infoblogs.com name servers, we get that CNAME record pointing to dualstack blah, blah, blah.amazonaws.com. Of course, Dig only chose one of the root name servers, one of the com name servers, and one of the infoblogs.com name servers to query rather than querying all of them, but that's understandable. Next, let's do a zone transfer. Remember that the query type that initiates a zone transfer is AXFR. Let's dig AXFR nxdomain.com, knowing that the first name server in the resolver configuration on this host is actually authoritative for nxdomain.com and will permit a zone transfer of nxdomain.com. If either of those things weren't true, we wouldn't be able to do a zone transfer. You can see we get a lot of output containing the entire contents of nxdomain.com, which is my personal zone. You can see that there are a bunch of things in here: a Windows 7 VM, the Wii, my son's iPad. So a lot of different stuff. Last, let's try an incremental zone transfer. The query type for that, you'll remember, is IXFR, but the query needs to contain the serial number. So we have to specify that after an equals sign. So let's say dig IXFR equals, and I happen to know in this case that the previous serial number looks like that in nxdomain.com. And the output, well, the output is a little tough to interpret, but basically this is giving us the diffs between that serial number, which is one previous to the current, and the current one. And you can see here that my mom's iPad has been removed from the network. So those are the basics of DNS theory. You have a namespace that contains domain names, which in turn point to resource records. You have resolvers and name servers, which cooperate to find arbitrary domain names in that namespace through a process called resolution, wherein they send a combination of recursive and non-recursive queries and follow referrals until they receive an answer. The data in the namespace is partitioned into administrative units called zones, and authoritative name servers load one or more of those zones from zone data files or from other name servers. The zones can contain a wide variety of types of resource records, including records that point to IPv4 and IPv6 addresses, mail routing information, and records that allow mapping back from addresses to domain names. Because resolvers and name servers usually send queries over UDP, the user datagram protocol, they may need to retransmit those queries or fall back to other name servers. And of course, there are query tools that allow you to query name servers yourself, including nslookup and dig. Believe it or not, there's lots more to the domain name system. There's name server configuration, zone data management, the DNS security extensions, the list goes on. But unfortunately, this is all we have time for now. Thanks a lot for watching.